So in the first half of this lecture, we figured out how we should set up Diffie-Hellman key exchange correctly to make Eve's brute force work as hard as it possibly can be. So that's why we must work with a prime P as a modulus and a primitive element G mod P. So suppose you do all that, why is it still safe to do this? There's so much stuff in Diffie-Hellman key exchange that's made public. It seems dangerous. So the question now is, all right, suppose you set up Diffie-Hellman correctly. So what? Why can't Eve still get the key from all that public information? Okay? If you remember what's public in Diffie-Hellman is the prime, the primitive, Alice's A, and Bob's B. And the only secrets are X and Y. So that's a lot of stuff that's made public. There are 4 things that are public. Can Eve get the key? The answer is no, not really, but it's not obvious why. Let's get into this. Let's pretend that we're Eve for a second, okay? Since we set up Diffie-Hellman correctly, she can't really brute force the exchange, okay? For really big primes, making a table like we did above in example 3 is just not realistic. But let's think about what Eve knows from Alice's side. And the analysis from Bob's side is exactly the same. So we only got to analyze it from one person's point of view. Okay. So what does Eve know about Alice's transmission? So she knows that Alice's secret number X obeys this rule here, that A must be G to the X mod P. Now think about what Eve knows. Of the 4 variables here, Eve actually knows 3 of them. She knows A, she knows G, and she knows P. That's all public information. The only thing Eve does not know is X, and she really wants it. So the question is, can't she just solve for it? I mean, it's an algebra problem. Can't Eve just do the algebra, solve for X, and be done? Then she can steal the secret and get the key? And the point is, isn't this exactly what logarithms do? So let's look at an example of ordinary logarithms that you might have seen in high school algebra. So let's look at a logarithm problem in example 5. So suppose we're in ordinary algebra, okay, real number algebra, no modulus stuff, okay? And we had the ordinary algebra problem 5 to the x is 20, which looks a lot like this. 5 to the x equals 20. Here's how you solve for x. What you do is you take the log, and let's just do base 10 for no good reason on both sides, and get the log of 5 to the x is equal to the log of 20. But then a property of logs says that powers up here can come down out front, and so log of 5 to the x is the same thing as x log 5. So this really right here says that x log 5 is log 20, sorry. So I can divide both sides by log 5 and get a solution. So I just solve for x. X must be log 20 over log 5. And if you work it out, you get that x is about 1.86131. Okay? So the question is, well, can't Eve pull the same thing off with A being G to the X mod P? And that would let Eve solve for x pretty easily, and amazingly the answer is no. It turns out that right now, as of March 31st, 2020, there is no way to do logarithms in a modulus. Logarithms are somehow a real number thing. They can't be done in a modulus, okay? So if there's a way to calculate logarithms in a modulus like mod P, no one has discovered it yet. Lots of very smart people have worked on this for decades, and they've made essentially no progress, okay? So this question of can you find an efficient way of computing what are called discrete logs is a famously hard math problem. It's so famous and so hard, there's actually a $1 million bounty on it. So if you can solve this problem, the solution's worth $1 million. This problem is so important that it has its own name. It's called the discrete log problem. Okay, here's the discrete log problem in its most general statement. Suppose I hand you the modulus and I tell you what it is, and I tell you the values of a and b in the equation a to the x equals b mod n. The discrete log problem asks, is there a way to solve for x, to solve for that exponent? Is there a way to solve for x by some algorithm that is sufficiently faster than just brute forcing it? Can you do that? That's the discrete log problem. Can you solve such an equation for x? If you know a, b, and n, can you solve such an equation for x by some technique that is faster than just brute forcing it? Okay? Now, of course, the brute force solution theoretically, mathematically works. There's only a finite number of exponents that could possibly work, so just check them all. But when the modulus is large, like it is in crypto, that's impossible to do, right? And that's why we have this clause here. You don't want to find some way that does it. You want to find a way that does it that is faster than just brute forcing it, right? So the discrete log problem is asking for a technique for solving for x that is significantly faster than brute forcing it, something that's fast enough to actually be dangerous in cryptography, okay? Now, to be clear here, this is a really hard problem, but people have discovered ways to solve it that are not brute force. There are ways to solve it that are definitely smarter than brute force. But the amazing thing is these smarter techniques aren't any faster than brute force. It still takes forever to do it. So even the really clever techniques, they take just as long to run as brute force does. So the problem with this discrete log problem is you want an algorithm that is sufficiently faster than brute force, not different than brute force. It must be faster than brute force. And amazingly, okay, this is the amazing part to me, no one has found a fast way of doing this, okay? And a lot of incredibly smart people have worked on this, and no one can do it. So, be careful. This does not mean that such a technique isn't out there. It might be that some really, really fast magic technique is out there. It's just that no one's discovered it yet, and this is dangerous. If someone discovers it, we're in big trouble. So right now, we understand, given current technology, why Eve can't simply solve for x in such an equation like this. If Eve could really simply solve for x in an efficient way, then she would actually be solving the discrete log problem, which no one on Earth currently knows how to do. So that's why it's safe. So here's the verdict. When you set up Diffie-Hellman correctly, its security is based on the apparent hardness of the discrete log problem. Okay? And I said apparent hardness because maybe it's not that hard. We just haven't discovered the solution yet. But we think it's hard. Okay? All the evidence shows that it's hard. And so that's why the Diffie-Hellman key exchange protocol is currently, as of right now, thought to be secure, is because its security is equivalent to the discrete log problem, and the discrete log problem we think is very hard, and therefore this must also be hard to break. Okay? But again, the technique could still be out there, we just don't know about it yet. So in other words, as soon as someone cracks a discrete log problem, we're in trouble, because then that also has a domino effect and it breaks Diffie-Hellman, and that would make it no longer safe for use. But so far, we're okay. No one has solved it yet, okay? So don't lose track of this, okay? This will not be the last time we see the discrete log problem. We are going to see it again, okay? Stay tuned.